Okay, yes, thank you. So I'm Francesco, I'm PhD student at CISA in Trieste. And I will still talk about mixed models with galaxy clustering. So I will just add a few motivations to the ones that Safak already gave. Here maybe with a slightly more particle physics angle. So actually, why galaxies should be sensitive to the properties of dark matter? Because this is what steers the growth of perturbations, at least at late times. So for BSM, this should be really an interesting observable. So actually, concerning the scales that one is able to probe, galaxies are actually probing somewhat an intermediate range of scales. So this is to say that crazy deviations from pure CDM are already constrained on one side by the CMB and also on small scales by Lyman alpha and weak lensing, for instance. So, but the advantage of galaxies in this sense is that they are the error bars are very tiny, especially with respect to the small scales, and have a very robust theoretical modeling. So this makes them the ideal probe for, let's say, precision tests of small deviations from pure CDM. Needless to say that if the dark sector is really dark, this might be a unique window, and I think this makes the effort worth it. So yes, so concerning the small deviations from CDM that we consider, there is this class of, this doesn't work, of mixed models. And there are a lot of particle physics scenarios that fall in this class, where the main component is still cold, as in the case of Safak. But there is another subcomponent that behaves differently. Actually, in almost all the particle physics scenarios, phenomenologically, the perturbation, provided very few assumptions solved, the perturbations of the second species can still be described with a fluid approximation. So the only additional relevant term that appears is this k-squared term, with this coefficient is the sound speed, and this actually entails a new scale, as was already mentioned. It's called the gene scale, the free streaming scales, depending on the physical origin. But in the end, constraining these models amounts at constraining a 2D plane, the fraction, and this new scale. So yes, these are the questions at linear level. So what happens at linear level is already very well known and implemented in Einstein-Boltzmann solver. And this is suppression at small scales, right? And I reported this in order to show that maybe, especially for these BSM cases, it's worth it to go beyond the pure geometric information and try to really probe this suppression with a full shape analysis. And one should get really better constraints just using background information. But to do so, one must first study nonlinearities in this case. So what we have to do is first a theoretical study of nonlinearities in these generalized scenarios, and only then we could move to apply to the data. So concerning nonlinearities in the fully first principle approach of EFT, these are computed with perturbation theory that is expanding in powers of the linear density field. And the new physics is expected to enter in these coefficients, the mod couplings that are called the perturbation theory kernels. Now, since this is a two-species problem, one will have also contribution for both species. For instance, if one tries to compute loops for chi, one will get the contribution from chi itself and also from the cold component. And in principle, here the coupling is completely unknown. It can be rather different from the pure CDM, mainly because in this problem there is a new scale. So in the scale-free problem of pure CDM, the kernels actually can only depend on the ratio between the two momenta. Here with a new scale, things can be rather different. So what we did is, what we were able to do is to study the limits where both these momenta are very far from this new scale, and analytically, and compare with the fully numerical solution. So what we're skipping a bit, what we found is that for several motivations, the new kernels are actually, for instance, for the second species chi, are actually very similarly structured to the Einstein de Sitter ones, provided that one expands on the second, on the chi linear density field. Or this can be rephrased as the fact that then the nth order in perturbation theory is actually extremely well approximated for chi, is actually extremely well approximated by just rescaling with the linear transfer function, the corresponding one for the cold component. And this non-trivially also for the velocity field. And this approximation has the nice feature that whatever cross-power spectra one may compute, higher cancellation always happens, at least at one loop. So we compared this approximation with the fully numerical solution for the matter power spectrum. And we found that it works better than 1%, even if the fraction is somewhat high, 10%. And if one naively expects that the error scales with the fraction, this will be for sure fine for all the realistic survey volumes, unless, of course, one will get a detection, which would be interesting per se. So, okay, say that we are able to compute loop integrals with the two species. We can, moving towards the constraint, we can embed this in the EFT framework. So concerning the galaxy bias, we do something simpler that what Safak presented. We had just actually let the galaxies trace the two growing modes, two linear growing modes, delta C and delta chi. And so we have an additional freedom at the bias level, B chi. And also we had to modify the code to implement the new functional forms that serve to cancel the UV sensitivity of these new integrals. So only when we have done that, we could finally feed the data. So we, as a proof of principle, we do this on the usual BOSS data. And of course, to do that, we have to choose a physical model. So what we did is we chose ultralight axions, if this turns okay, mainly because we had a reference. So actually, the two parameters are the mass and abundance, but really the mass can be treated as this new scale that I'm reporting on top. So this is the result for the exclusions. So in red, Planck is Planck only. So when adding BOSS, but still with one fluid only modeling, but we are really constraining the second component, one gets the dashed line exclusion constraints. But when one does things more carefully with the two fluid modeling, we see that the constraints degrade is the solid line. And this is expected, of course, right? One has more freedom and more parameters. But actually what happens is that for some value of the masses, careful modeling makes it lose all the training power with respect to Planck. Yes, so, okay, to give instead a positive message, maybe I can mention the importance of this mu equals 0 observable that was mentioned yesterday. So the advantage of this is that it's free of registry-space distortions and can be pushed to higher scales. And I'm showing this because maybe this is even more rewarding than for, okay, works. Than for CDM. Because see, for a specific value of the mass, just by adding Q0 more scales, the constraining power increases impressively, I would say. So this is nice. It shows that the constraining power here is really coming from probing the shape suppression, which I think is nice as well. So maybe looking at new is especially relevant for BSM. So the conclusion in the end is that while CMB plus LSS, the combination is already extremely powerful, it reaches to exclude already a 1% fraction. Theoretical modeling has to keep up with that, as was also shown by Safak. Not to overestimate the constraint, but especially in case we will get a detection of a non-null fraction, this would be imperative. So in the meantime, there are a lot of other ways that one can pursue. For instance, the number of new parameters and counter terms explodes in these scenarios. So maybe it's even more, it's also very important for BSM to have motivated priors on these new parameters. And of course, maybe there are several other particle physics scenarios that fall in this class that can be probed and constrained with galaxies. That's it. Thank you. Ecco, sentiamo. Mm-hmm. Mm-hmm. Okay. Okay. Mm. Exactly, yeah. I mean, yeah, the difference will scale as the error bars against the small difference. So, but if you have smaller error bars, you will get a bigger difference, maybe, I guess. But anyways, the thing is that at late times, when you go to high masses, they become even really a too cold fluid system. So maybe that's the reason. So it's two fluid model, but actually are both cold. So I mean, the description is the same as a one fluid. It's not non-important. They are the same as pure CDM. Maybe. So they are. The difference with respect to pure CDM probably is not important. Yes.
Max was 1, let's say, you make this constraint, let's observe it at 4. Now, on this end, you can push a lot more. This I understand. So for me, the region where I would expect the biggest deviation from linear theory is when the gene scale approaches the nonlinear scale. Because it's, of course, when it's larger, we all agree that there is the cap.
But indeed, if the linear scale is 0.5, maybe, yes.
So there you're already in there.
Yeah.
And in the middle, why? Okay, so and in the middle. Okay, so
exactly.
So the middle is one in that direction.
Yeah, they're very different, indeed. Yes. Because the two fluids are very different, so the different bias parameterize different shape, and one gets the difference.
The effect is purely in the bias, or you get effect also from non-linear?
I guess the main effect will be in the bias, yes. But yes, if you compute everything like CDM, you will find no difference when varied that to biases. I think to say that the difference in the linear corrections there are relevant, I would say, yes.
So I will ask the executive So, okay, I think let's find that.
Here on this side, okay, yes. Yes, exactly. But here, okay. So here the relative mode is exactly the same as the growing mode. So, because one species is not there, so delta relative is equal to delta C if you want somehow. So the perturbations of the second species are 0 here, de facto. So I mean, it's again really, here it's like for neutrinos, no? Here. Totally free streaming. For the scales that you probe, the second species is totally free streaming, and again, the perturbation that grows is only one species. No, but the effect is should be very tiny respect to that. Yes. Exactly. Yeah. Yes. Yes. No, exactly. Indeed, we do the most agnostic thing, which is the second one. Yes. Actually, we thought about that, but I mean, for the moment, we just let all the parameters vary from minus infinity plus infinity, let's say. And so, but yes, one would expect for instance, indeed, the bias in the cross power spectrum to be order of diffraction and so on. But we really allow for instance, this BK here to take even large values compared to also comparable with B1. So yes, we really let one fluid substitute the other when varying it, which is unrealistic if the fraction is small. But, so we try to do that. One gets okay, a stronger constraint, but still different from the, even if you assume that all these other parameters are order of chi, so maximum 10%, still there is a losing constraining power. Is it somewhat in the middle, the line will be, between the solid and the dashed, yes. But one has to... Information, exactly, yes. Yeah, definitely. And it, yeah. Yeah, totally true, yes. Mm-hmm.
That the error on the delta of the new species or the error in the power spectrum?
No, and error in the total power spectrum. Now, the new species, we have a bigger error, but since the fraction is small, the total power spectrum gets fraction times this error, essentially, yes. But if we expect the galaxies to be correlated with the total matter, maybe this is fine, yes. If galaxies turns out to trace completely the second component, this will not be fine anymore, yes.
Okay, so let's thank Francesco again.